All right, I think I'm doing that. Okay, good. So when axial force is present, okay, my equation changes slightly. So BC equal to a 2 bracket inside 1 plus mu divided by a 2000 Ag, okay, and outside is lambda square root f prime c BWD. Okay, now the only new parameters here, mu, is applied moment. Well, I shouldn't say that, I should say factored, okay? Factored moment. And Ag is the gross cross-section area. Okay, now this is when axial force is present. What I mean by the axial force is present, namely, I will have a beam support like this. Have distributed loading, sure, fine. And I have diagonal crack, and this is where I'm considering my shear design for. And then I also have my axial force like this. Axial force like this. Okay, sorry, this is not mu anymore. Make a correction here. This is NU, the axial force, okay? NU. This is now factor moment. Sorry, this is factor axial force. Factor axial force. Okay, so this is NU. NU. Okay, now if you look at the equation here, now let me say NU is positive when compression is present. Okay, and NU is negative when tension. So this is positive and this is negative. So this is positive right now, okay? And what does it mean? Means that in my equation here, I'm just going to use red, okay? If I have positive NU, which means compression, I will increase my shear. So if NU in positive, when increases, my shear resistance of the concrete increases. Okay, you can think of it when I apply an axial force, it will tight up and try to close my crack. Okay, and enhance aggregate interaction to enhance my shear resistance. On the contrary, if my NU is a negative, and when it increases, my shear resistance from concrete drops. Okay, my shear resistance from concrete drops. And also, you can find this equation from ACI. From this equation from ACI 2020, sorry, 22. 0.5, 0.5, 0.1. Okay, these for the axial forces. Now, I have to say, if I have a tension force, right, for axial tension force, right, my equation changes slightly as well. So let me go back. So if VC would equal to 2, same thing here, 1 plus NU divided by 500 AG. Okay, and lambda square root of prime C BWD. And this, let me just say, let me add something here. So this is when NU is positive, or NU is positive or compression. And this is when NU is negative or tension. Okay, equation changed slightly, and the main change is right here. Right here. Okay, you notice that this number 500 is smaller than 2000. Means if I have compression force, the enhancement to the concrete shear resistance is small than the reduction of concrete enhancement in terms of tension force. Okay, all right. Okay, so this is all the equation you need for designing shear. So let me label them out. Okay, so I have equation 1, so let's call it VC1, VC2, VC3, running out of space. Okay, so I'm just going to write here VC3 and VC4. Okay, So let me see which slide number 5. Okay, 5. So now we have VC1. You can make a tiny table, isn't it? So this is moment known. Okay, and VC2, nothing is known, so all unknown. And VC3, compressive axial forces. And VC4, tensile axial forces. So you select different equation based on the condition. All right, you select different equation based on the condition, because this is VC. Okay, this is the concrete shear resistance, or shear resistance from the concrete. Okay, so the slightly messy because it has 4 different set of equations, but normally this is the mostly used equations. Okay, mostly used equations of VC2 equal to 2 lambda square root F prime C B W D. Okay, so now this is the mostly used equations. And in the exam, you see this equation most of the time. Okay, see this equation most of the time. All right, now we have covered how we compute the shear resistance from the concrete. What about reinforcement, right? What about reinforcement? So let's go back and talk about reinforcement. Slide number 6. And shear resistance from steel. So shear resistance from steel, okay? From steel. All right. Now, there are 2 conditions as well. So let's talk about VS1. So VS1 means with vertical stirrups. I always have trouble spell the stirrups. Stirrups. Okay, vertical stirrups. So what is vertical stirrup? This is what it is. Okay, so I'm going to draw this diagram in terms of blue, so differentiate a little bit. So now I have again, free body diagram like this. My support is right here. Vertical horizontal bars at the bottom, and vertical stirrups like here. Okay, and then I'll have several parameters or designations. Okay, so let me just say all my shear stirrups, has a spacing of S. Okay, spacing of S. All right, and I'm going to assume, I'm using a red line here, I'm going to assume this crack direction is roughly 45 degrees. 45 degrees, okay? If that's the case, I have a depth of D here, and when it's 45 degrees, the opening here is also D. Opening here is also D, okay? So now each one of them, right? Each one of them will give me a tension force, right? And this is AV FYT. Okay, explain, right? Explain, excuse me. What is AV and what is FYT? So AV is the area of the legs of stirrups. Okay, how so? Now I'm going to try to draw a 3D drawing of stirrups. So 3D drawing of stirrups gave me the stirrups like this. Sorry. Try my best to draw it here. Okay, so this is the stirrups if I look in 3D. Okay, and this will be my concrete. Okay, concrete, and have another stirrups like this, right? Okay, and also I have, no, this is the, I have longitudinal reinforcement to connect them, right? I have longitudinal reinforcement to connect them, assuming I have also compression bars, all right? So that is in the cage, right? That is in the cage. And when I say AV, right, I'm going to use a rect cut. When I say AV, I'm cutting here. I'm also cutting here. Okay, so for a stirrups like this, when I make cut, I cut 1, 2. So two legs. All right. Why so important? Because say a number 3 bar, one leg gives me a 0.11 inch squared. A leg, AL. Okay. I have another one is 0.11 inch squared. So AV actually go to 2 legs. So 0.22 inch squared. Okay, so be careful here. Okay, be careful here. I actually have two legs. Okay, 2 legs. All right. Okay. Now some student asked me which one was VC1, right? VC1, right? So you can go back to the notes, which I'll upload quickly, right? VC1 is this equation right here. Consider the moments, okay? Which we do not use often. We mainly use VC2, okay? Again, you have all the notes. I'll upload them shortly, okay? Now coming back, so AV is area of the legs of the reinforcement, okay? So 2 legs normally. All right, so be careful here. FYT, what is FYT? FYT is the yield strength of stirrups. Okay, so now we have all the information we need on this crack. So the total shear resistance provided from reinforcement, right? So I want to write this way. So VS, the total shear reinforcement provided by steel, equal to the total number of stirrups in the spacing D. And this is the D here. Okay, spacing D. Use the right color. Okay, in D. So how many stirrups I have in the spacing with D, right? So that's the critical thing. So let's do a calculation, right? Let's do a calculation. So now I actually can count, right? The number of stirrups in the diagonal crack, diagonal crack, spacing D, equal to what? Equal to S. Sorry, actually equal to what? Equal to the spacing D divided by the stirrup spacing S. Okay, stirrups spacing S. So given this, I can immediately get equation. The shear resistance from steel Vs equal to what? A V FYT. That is the shear resistance per stirrup. Okay, multiplied by number of stirrups in the diagonal crack zone. Diagonal crack zone. All right. Okay, so now I have the shear resistance from the vertical stirrups. Okay, now be careful. This is 1. Okay, this is scenario number 1. Vertical stirrups. Okay, so this slide number 6. Let me go back to black color. Okay, 7. Sometimes I do not always have vertical stirrups. I sometimes have AVS2, which means inclined stirrups. Okay, so I'm going to draw it the same free body diagram here. However, now this time my stirrups goes this way. That does not change the fact that each stirrup will still contribute AV FYT. Okay, and the inclination angle here is defined between the stirrups and the horizontal bar, so alpha. This is reaction force here, okay? So alpha right here. All right, and now spacing between this is still counted as the horizontal distance, okay? Horizontal distance between the vertical stirrups. And the equation to calculate the shear resistance from that basically tells you is Vs2 equal to AV FYT multiplied by, multiplied by sine alpha plus cosine alpha multiplied by D over S. Okay, now the detailed derivation, you can find it from textbook. Detailed derivation of this equation can be found in the textbook. We simply are not going to cover here, okay, because it's just out of scope, and we'll talk more later if you're interested, okay? So now, if it's inclined, the equation becomes this. So I want to summarize, right? I can say the shear resistance Vs also has two possibilities, Vs1, Vs2, and Vs1 is for vertical stirrups. Vs2 is inclined stirrups. And again, once again, we mainly use this one, right? So mainly use the vertical one, and that is AV FYT DS. Okay. All right. So now we are covered. Right? We're covered. Okay. Now, coming back. Let's circle back on the question we raised at the beginning. So now the whole design concept for shear requires that phi, Vn, is greater or equal than Vu. That is equal to phi, bracket inside Vc plus Vs has to be greater or equal than Vu. Applied shear, factor of shear, okay? Factor of shear. All right. Hence, there's a question. What if the resistance from concrete only Vc multiplied by the stress reduction factor 0.75, of course, has already exceeded Vu, right? Has already exceeded Vu. This means, does it mean? Does it mean no stirrups is needed? Now, unfortunately, the answer is no. Answer is no. Okay, because since shear is a brittle failure, so since shear failure is brittle. Okay, now recall the definition. Brittle means once it failed, you have no time to run, right? Immediately collapse. So reinforcement, minimum reinforcement, okay? So AS, right? AS, now I like to say AV, minimum, is required. The minimum amount of shear reinforcement is required, okay? And now you can find this from ACI 9.6.3. Oh, sorry. Oh, shoot. Okay. Pardon me, I'm still trying to get familiar with this, okay? AV mean is required, okay? So per ACI, it actually says when, so if Vn, okay, Vn is our VU. If VU applied shear is bigger than half of VBC. Okay, be careful here. That means if my applied shear is bigger than half of the concrete shear, okay, if my applied shear is bigger than half of what the concrete can provide, I require AV mean. Okay, and AV mean equals 0.75 square root F prime C BW stereo spacing S divided by FYT. Okay, and then also it says even this has to be bigger than 50 BW S divided by FYT. Okay, BW S and FYT. All right, such a stringent requirement means let's put some shear stirrups even if you don't need it. Okay, as long as the applied shear is bigger than half of what concrete can provide, put stirrups in it. Okay, this is very important. Okay, very important. Okay, so there are exceptions, of course. Okay, and you can find them from 9.6.3.1. Okay, and actually I have it ready. So let me stop here and share you with my ACI code. Okay, with my ACI code. All right, so let me try to do this. Okay, so if you can see my screen and I'm sharing my ACI code. Okay, now I'm talking about 9.6.3 minimum shear reinforcement, right? Blah 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 blah. However, this table 9.6.3.1. Okay, I'm trying to highlight here. Okay, we do not have to satisfy the requirement if my applied shear is smaller than VBC. Okay, so go to your ACI 318.19. Find this table 9.6.3.1. These are exceptions. Okay, these are exceptions. Okay, see text messages. No, I have not gone over the midterm scaling yet. Okay, I'll talk about end of the lectures. I know it's very interesting, important, but I think shear is also equally important. Okay, and yes, the Zoom lecture is being recorded right now. I believe the red dot is shining, and I'll upload them afterwards. Okay, but still, I think it is important you keep up with the lecture. Again, the homework due date I already released online through email. I'll repeat it again after this lecture. Okay. So coming back, we need this table. We need this table to know the exceptions. All right. We need this table. So let me stop sharing here and go back to my screen. Okay. So let me do this. Me running again. You can see it. So you can find that this table 9.6.3.1 for minimum ring for exceptions. Sorry, it's already written here for exceptions. Okay. So I'm just gonna save room here. Talk about it here. Okay. All right. So now we have a clear plan of how we design shear reinforcement. So slide number 9. Different color. Slide number 9. How we do design. So here, design of web reinforcement. Okay, web reinforcement. All right, so VU, we know, has to be smaller than VVN. That is smaller than VVC plus VVS. Okay, that means my reinforcement provided shear or shear from reinforcement VS has to be greater or equal than VU divided by phi minus VC. Okay, in this case, for vertical stirrups, okay, VS known equal to AV FYT D divided by S. So I know solve for S required Okay, spacing, the spacing has to be smaller than AV FYT D divided by VU divided by V minus VC. Okay, what does this equation mean? Okay, this means normally we design for spacing, stirrups spacing, given size of the stirrups. Given size of stirrups. Because in the field, normally the size of the stirrups is fixed, is constrained. It's constrained. We only have control over the spacing. Okay. Now, correspondingly, if the stirrups inclined inclined stirrups, the required spacing equation changes slightly. It has to be smaller than or equal to AV FYT spacing D, diagonal cracks length D, sine alpha plus cosine alpha, and this alpha is the inclination angle divided by VU divided by V minus VC. Okay, so this is the equation for vertical. So for inclined stirrups, and just put a notation here. So the stirrups go this way, and alpha angle is defined this. Okay, defined this way. Okay, so these are the spacing requirements to put up the stirrups. However, also there are minimum requirements. There are minimum requirements. Okay, what kind of minimum requirement? Now think of it. Think of it. If I have a free body diagram, like the diagonal crack shown before, right? And I have stirrups spacing this way. Even if I satisfy the spacing requirement, say this is required. Okay, I still have a situation. What type of situation? Assuming my diagonal crack is going to go this way, and it has a 45-degree angle. 45-degree angle. All right, 45-degree angle. I have to make sure. There is at least one stirrups in the spacing D. If at least have one stirrups, that means if I at least have one stirrup, that means, okay, that means this is required, and this is D. And this fellow here is the one stirrup that in the middle of the D. In the middle of D. That means what? That means 2S required. Sorry, 2. Hey, why am I using different color here? 2S required has to be smaller than D. Okay, so that means S required has to be smaller than half D. Has to be smaller than half D. So that means on top of all these required spacing equations, okay, required spacing equations, right? I also have to make sure my S max, the maximum spacing between stirrups, has to be lesser of two parameters. Either has to be D divided by 2, and per ACI also 24 inches. Okay, 24 inches. And this you can find from ACI 9.7, 0.6, 0.2, 0.2. Okay, so now that is the maximum spacing requirement, means the maximum spacing you can put your stirrups after it satisfies the spacing requirement for calculation. Okay, calculation. All right, so our time is up. I'm going to stop here. So quickly about midterm scheduling. I don't really know when are we going to take the second midterm yet as it is, because we have to evaluate by our progress. But let's just safely say it should be within 3 weeks, because we'll have the final approaching soon. And then also we'll probably cover mainly the shear and TB. Okay, so as soon as we finish the shear design, we'll talk about the midterm exams. And again, midterm will be in terms of take home. Okay, however, for the take home, we have a specified time period for you to finish the exam. That means I'll release the exam on particular time, and I give you exactly the time needed to submit it, to finish it, and you will have to submit before this time period. Okay, and to make sure it's a fair exam, I will make the problem a little bit longer, but trust me, it will be easy for you to comprehend and solve. Okay, now to make the exam more fair, I will try to control over the time, so it will be not too long, so you can solve the problem efficiently. Okay, so that's all I have to say on the exam. For the homeworks, since we have extension, the homework will be officially due this Thursday. Okay, so the specific time, specific date, let me see here, is April the 2nd by midnight. Okay, let me say this again. The homework number 4, homework number 5, new due date will be April the 2nd midnight. Okay, thank you very much. I am going to end the lecture now, and I will upload lecture notes to Canvas. Same time, I will upload the recorded video to YouTube as soon as I can today. All right. Okay. If you have any question, feel free to email me or just send me a chat. All right. Thank you very much. I'll see you tomorrow, Tuesday at 2 o'clock for our office hours. All right. Appreciate it, and have a safe day. All right. Bye now.